Got it, please. Let's go around the horn, and I'll assume if you give me a go, you've got no instrumentation problems. Booster? Go flight. Retro? Go flight. Fido? Go flight. Control? Telcom? Go. GNC? Ecom? Capcom? Go. Surgeon? Go. ONP? Go. ASD? FAO? Go. Network? Go. You got everything up? Go.
Hello, I'm Ian Christie, and this is Terranauts. Today, as part of the Terranauts Guide to Leaving the Planet, we're going to complete our look at rocket science. I will point out that this is the second part in a two-part series, so if you haven't listened to Rocket Science Part 1, you may want to go back and do that before you listen to this episode. In Part 1, we talked a bit about the basics of rocketry and the history of primitive and early rockets up to the beginning of the 20th century. You'll recall that I said there were two fundamental things you need to know about rockets in space. The first is that there is no air in space, and the second is that a rocket is really just a bomb with a hole in one end. Today we're going to add one more to these Christie's rules of rocket science, and that is that getting to space is not about getting high, it's about living fast. I'll explain later. Let's proceed. At the time where we left off, the late 19th century, the science of rocketry had not really come very far in the 6 centuries or so since the first rocket was invented in China. Rockets were basically black powder bombs with a hole in one end to let out the expanding gases, and they were usually attached to the tops of long sticks, which were used as a primitive way to give them some stability so they would be slightly more dangerous to the people they were pointed at than to the people who were launching them. Except for maybe some use for fireworks in China, rockets were basically used for military purposes, but since they were both less accurate and less powerful than artillery of the time, the technology wasn't really advancing. The early shift to what we might call modern rocketry actually came from outside the military. In fact, it came from outside science and engineering entirely. It came from science fiction. Rockets were just prominent enough in the latter half of the 19th century to inspire authors such as Jules Verne and H.G. Wells to write stories that imagined the possibility of humans using rockets to leave the Earth, or for extraterrestrials to use them to visit Earth. With this sudden interest in the possibility of using rockets to leave the planet, a small number of engineers and scientists started to apply some genuine analysis to the problem. One of these pioneers was Konstantin Tsiolkovsky in Russia. Tsiolkovsky was born in 1857 in a log house in a village southwest of Moscow. Because of hearing loss that he suffered as a child as a result of scarlet fever, he wasn't able to attend elementary school. He was homeschooled and self-taught. As a teenager, he was inspired by Jules Verne's writing, and he began a lifelong work in laying the mathematical and physical foundations for the possibilities of human spaceflight. One of Tsiolkovsky's enduring contributions was to write down something called the delta V, or rocketry equation. This same equation was independently derived by Robert Hénault Pelterie in France, another of the early modern rocket pioneers. This equation has literally been the starting point for almost every rocket engineer that wanted to leave the planet right up until today. So, what is the delta V equation and why does it matter so much? Well, let's break it down. First of all, the V we're talking about here is velocity. So why velocity and not speed? Well, speed is what math nerds call a scalar, and velocity is what those same nerds call a vector, which just means that it has a direction as well as a magnitude. Now, so long as you're moving in a straight line, there really isn't any difference between the two. Once you start moving in a curve, and everything in space moves in a curve, it's important to consider direction, so we're going to talk about velocity. Secondly, delta is a Greek letter, but it's also the symbol that mathematicians and physicists use to denote the change in a quantity. So, delta V means change in velocity. Now, the delta V equation says that, in the absence of any other interactions, the change in velocity that any rocket can achieve is directly related to the exhaust velocity of the gases that come out of it, and the initial mass of the rocket divided by its final mass after all of the rocket propellant has been used up. Okay, so why does that matter? Well, this is where our rule for today comes in. Contrary to what you might think looking up at the night sky, getting to space is not about getting high, it's about living fast. In other words, the secret to getting to space is not to go up, but rather to go really fast. The reasons for that have to do with terms like centripetal force and angular momentum, and other things that I don't want to go into here because they're probably going to be the subject of their own episode at some point. Suffice it to say, though, that with a little bit of math and physics, you can calculate just how fast you actually have to go to get away from the gravitational force of any planet or star or other celestial body. And it turns out that for the Earth, that escape velocity is about 11,000 meters per second, which is almost 40,000 kilometers per hour or 25,000 miles per hour, or something in excess of 30 times the speed of sound. So, like, really fast, dude. It turns out that in addition to characterizing how hard it is to get away from things, you can also use a delta V statistic to characterize how much effort it takes to do other useful things in space, things like getting into orbit around other planets or the moon, or slowing down enough to land on the moon or another planet. So delta V is a very handy way of specifying the performance you're going to need out of a rocket. But it's still kind of a funny quantity. Change in speed, measured in meters per second or kilometers per hour. These aren't quantities that even those of us who remember high school physics think of as being related to the power of a rocket engine. But it turns out that Isaac Newton has something to say about that, and if we engage in a bit of physics sleight of hand, we can see why it works. See if you can follow this logic. Acceleration is what we call a change in velocity. Speeding up or slowing down is acceleration. So a change in velocity results from an acceleration that's applied over a period of time. The longer we accelerate, the faster we go. Okay, so we can also see that the delta V is equal to acceleration times time. Okay, so far? Well, Sir Isaac also told us, or at least told high school physics students, that if you apply a force to an object, its acceleration will be equal to the force divided by its mass, which makes sense. The heavier something is, the harder you have to push it to make it go. So, acceleration is equal to force divided by mass. The shorthand that math nerds use is acceleration equals force over mass. Okay, so now we know that delta V is acceleration times time, and acceleration is also equal to force over mass. So delta V is equal to the amount of force applied to an object times the length of time for which it is applied, divided by the mass of the object. All of which is to say that we now know that if you want to get to space, you need a rocket engine that generates a lot of force, burns for a long time, and doesn't weigh very much. And, according to the rocket equation, the best way to do that is to burn stuff that doesn't weigh very much and exits a rocket very fast. It is also critical to make sure that the rest of the rocket, other than the propellant, weighs as little as possible. So now, rocket designers had a theoretical basis that allowed them to characterize the performance of their rockets, especially when they were interested in using the rocket to leave the planet. Now, before we talk about the early modern rocket designs, let's first revisit briefly how a rocket engine operates. As we talked about in the last episode, there are three basic phases in the operation of a rocket engine. First, the propellant, consisting of fuel and oxidizer, has to be fed into a combustion chamber and compressed. Then the mixture has to be ignited, and finally, the expanding gases have to be exhausted out the back to generate thrust. In short, these three phases are often referred to as squeeze, bang, blow. Also, to put it in perspective, in 1900, the only existing rockets used black powder as a fuel and oxidizer, so the squeeze part was actually handled in the manufacturing of the powder itself. The combustion chamber was just a tube, and it is estimated that the efficiency with which these rockets turned combustion into thrust was about 5%. Folks, that is a long way from a Saturn V main engine. Enter Robert Goddard. Robert Goddard was an American physicist and engineer who was born in 1882 in Worcester, Massachusetts. He read H.G. Wells' War of the Worlds when he was 16, and by age 17 in 1889, he was obsessed with the idea of finding a way to, quote, make some device that had even the possibility of ascending to Mars, unquote. He would dedicate the rest of his life to advancing the science and engineering to achieve that end. In 1919, he produced another of the seminal works of modern rocketry, a monograph titled A Method of Reaching Extreme Altitudes. It is interesting to note that while the paper is now considered to be a classic, at the time it was widely mocked. In fact, a New York Times editorial in response to the paper said that Goddard's claim of being able to use a rocket to go to the moon was, quote, to deny the fundamental laws of dynamics, unquote. And it is also interesting to note that on July 17, 1969, the day after the launch of Apollo 11, the Times printed a retraction that read in part, quote, further investigation and experimentation have confirmed the findings of Isaac Newton in the 17th century, and it is now definitely established that a rocket can function in a vacuum as well as an atmosphere. The Times regrets the error, unquote. So, Dr. Goddard may have had the last laugh, but at the time it didn't do much for his desire to share his work. In fact, Goddard is reasonably renowned for his secrecy, and much of what we know about his early work was actually learned well after the fact. In the 1920s, Goddard started experimenting with liquid-fueled rockets. The reason for moving to liquid fuel was to overcome the fundamental limitation on the amount of combustion energy you can get from gunpowder. In other words, Goddard took a look at the delta-V equation and realized that the thrust over time that you could derive from a kilogram of gunpowder would never allow the rocket to reach the speeds needed to leave the planet, or even to get anywhere near it. His early rocket designs, though, look very strange to the modern eye because they retain the basic form of the black powder rockets, with a combustion chamber at the top of the rocket and the fuel tanks below the nozzle. In other words, the opposite arrangement that is actually used today. Using such an arrangement, Goddard became the first person to successfully launch such a vehicle in 1926 in Auburn, Massachusetts. He used gasoline as the fuel and liquid oxygen as the oxidizer. The flight lasted 2.5 seconds, and the vehicle traveled 184 feet. With continued testing, Goddard eventually figured out that a configuration with the fuel and oxidizer above the combustion chamber and the exhaust nozzle was not only workable but preferable. And of course, this is the geometry that we continue to use today. Now, speaking of exhaust nozzles, one of Goddard's principal contributions to rocketry, which is often glossed over in the literature, is his work on the blow phase of the rocket engine. Very early on, he realized that the low efficiency of primitive rockets was because of the design, or lack thereof, of the nozzle. Essentially, early rockets just spit the expanding gases out the bottom end while they were still expanding, quickly. This meant that the rocket lost contact with the gases while they still had a lot of energy gained during combustion. Goddard's innovation was to use a so-called Laplace nozzle, whose shape was designed to let the gases expand, but to allow them to continue to push on the rocket as they did so. As a result, he improved the efficiency of his rocket motors from around 5% to around 65% almost overnight. In fact, while quite a bit of design thought continues to go into the nozzle of a modern rocket engine, the designs are still part of a general family of Laplace nozzles, and the efficiency of these nozzles is certainly better than what Goddard achieved, but only incrementally so. So, by the 1920s, the blow part of the sequence had more or less been solved, or at least brought to the stage of modernity. Squeeze and bang, on the other hand, would be another matter altogether. Although Goddard pioneered many of the methods of solving these problems, the true breakthroughs that led to a rocket engine that could, and did, eventually lift man-made objects into space came in Germany. And it's here that we need to pause to acknowledge a dark chapter in the history of rocketry. There is no denying that the modern spacefaring rocket achieved its basic form in Nazi Germany in the 1930s and 1940s. There is also no denying that those fundamental breakthroughs were achieved in the development of a weapon that eventually killed thousands of people, including many thousands of slave laborers who were used to build the rockets themselves. Those are the facts. They have been explored elsewhere in great detail and with much more scholarship than I could ever hope to provide. If you're interested in the story, I would certainly recommend the book, The Rocket and the Reich by Robert Neufeld. The German rocket program had a fairly humble beginnings and started with a group of amateur enthusiasts in the 1920s in the Weimar Republic. Eventually, this group came to include a young German engineer named Wernher von Braun. Von Braun would become not only the father of modern space rocketry, but arguably the world's first Terranaut. In the 1930s, once the Nazi Party took over the German government and began rearming Germany, this amateur group would be subsumed into the German Ordnance Department, and with von Braun as technical director would, in October 1942, from a site at Peenemünde on the Baltic coast, launch the very first man-made object to leave the Earth's atmosphere. Of course, the rocket that we're talking about was the V-2 rocket, which Germany eventually deployed against London and Antwerp in 1944 and 1945. For most of its development, however, it was known as the A-4. It is quite literally the ancestor of almost every rocket that has ever left the planet, and many rocket engines in use today still owe a great deal to the design of the one that powered it. In his book, Robert Neufeld estimates that the effort to design and manufacture the A-4 required an investment of resources that for Germany's wartime economy was roughly equivalent to the effort expended by the U.S. on the Manhattan Project that led to the atomic bomb. In short, going from the first liquid-fueled rockets of the late 1920s to a vehicle capable of leaving the atmosphere required a massive amount of research, development, and engineering. So where did this effort go? What were the problems that needed to be overcome? Well, first, let's take a look at the scale of the problem. Robert Goddard's first liquid-fueled rocket was a couple of meters in length and weighed a few kilograms. Its motor produced probably a few kilograms of thrust and burned for a few seconds. In its first flight, it traveled about 60 meters. The A-4 was, by comparison, a massive vehicle. It was 14 meters in length, 1.6 meters in diameter, and weighed in at 12,500 kilograms, of which about 9,000 kilograms was the fuel and oxidizer. The A-4 consumed fuel and oxidizer at almost 125 kilograms per second and produced 25 tons of thrust at sea level, 29 tons of thrust at the top of its trajectory if you're keeping score. This motor accelerated the rocket to speeds in excess of Mach 2.4 and to an altitude of more than 100 kilometers, and it had a range of more than 300 kilometers. So, where to begin in describing the development path? Well, let's go back to our 3 phases of rocket propulsion. We already mentioned that Robert Goddard had done a pretty good job at sorting out the blow phase by using a Laplace nozzle design. The A-4 improved on this, but not markedly. So let's look at the bang stage. That's where most of the action appears to be anyways. Before we go much further, it's worth pointing out that contrary to what you might think, the science of rocketry is as much about chemistry as it is about physics. At its heart, the bang phase of a rocket motor is about finding chemicals, a fuel and an oxidizer, that are at least moderately stable on their own, but when combined result in a mixture that reacts easily, exothermically, and violently, and which produces a large volume of gas, preferably made up of relatively light constituents. This last part is important because, of course, the delta-V equation tells us that we get better performance the faster the exhaust travels, and lighter molecules are easy to accelerate than heavy ones. Rocket propellants over the years have ranged from the frankly pretty mundane, like alcohol and oxygen, to the truly exotic, red fuming nitric acid or pentoborane, anyone? For a complete and detailed dive into this world, I would direct you to the book Ignition by John D. Clarke, in which the subject is quite literally dissected in as much detail as anyone will ever need. To put the whole topic in perspective, Isaac Asimov wrote in the foreword to John D. Clarke's book Ignition that, quote, "There are, after all, some chemicals that explode shatteringly, some that flame ravenously, some that corrode hellishly, some that poison sneakily, and some that stink stenchily. As far as I know, though, only liquid rocket fuels have these delightful properties combined into one delectable whole." Unquote. In the A-4's case, the propellant system was pretty mundane. The fuel consisted of a mixture of ethanol and water, and the oxidizer was liquid oxygen. This was fairly similar to the original gasoline-oxygen mix that Robert Goddard originally used, and actually quite similar to many modern rocket motors that use oxygen and kerosene. The choice of alcohol appears, in fact, to have been driven less by design considerations and more by the fact that the fuels, like gasoline, were actually quite hard to come by in wartime in Germany. The problems really started when the kinds of quantities needed to produce significant thrust were actually compressed and ignited. To put it bluntly, they produced a lot of heat. Like, really a lot. In this, a lot is defined as enough heat to basically melt any known material that could be used to contain the reaction. Rocket engineers refer to this problem as burn-through. Non-rocket engineers refer to this problem as, wow, that blew up really big. In short, it was rapidly discovered that once we moved on from gunpowder, it was pretty easy to generate way more energy in a container that could reasonably be contained by that container. This is particularly a problem since the rocket equation continually reminds us that every kilogram of weight that is not burned by the engine reduces our ability to hit those delta V targets that we need to get off the planet. So clearly the problem cannot be overcome by throwing more metal at it. Instead, the effort went into finding a way to keep the combustion chamber cool. In the end, two techniques were developed to do this. The first is something called regenerative cooling, which is just a fancy way of saying that the rocket propellants were circulated around the outside of the chamber before they were sprayed into it. Since both alcohol and liquid oxygen are pretty effective coolants, this goes a long way to keeping the chamber below its melting point. But on the scale of even the 4.5-ton motor, which is a fifth of the size that was needed for the eventual A4 vehicle, it was found that this was just not enough to avoid catastrophic overheating. The second method of cooling, as odd as it sounds, was actually to spray even more alcohol into the engine. Except in this case, the alcohol was not sprayed in as a fuel at the top of the combustion chamber. It was sprayed around the edges of the chamber and the nozzle, and it was found that the alcohol would actually form a thin film on the metal surfaces, and this film provided enough insulation to keep the sides of the chamber from burning through. All of this sounds reasonably simple to describe, but as you can imagine, there were likely a long series of fairly exciting experiments that led to the perfection of these techniques. Another significant problem that needed to be overcome was ensuring that the combustion started smoothly and proceeded uniformly, or at least predictably. Anyone who has ever tried to light a gas barbecue with the top down will have experienced the result of having too much fuel and oxidizer present when ignition is initiated. I am sure that you will agree that the results can be impressive, though perhaps not entirely desirable. Rocket engineers refer to this phenomenon as a hard start. Likewise, having a combustion reaction whose rate fluctuates or having combustion chamber in which there are significant pressure variations or waves can result in situations that would best be characterized as highly undesirable. Needless to say, the bigger you make the chamber and the more of the propellants you attempt to stuff it into it, the worse the problem becomes. In the end, an immense amount of effort went into the design of the fuel injection system to ensure that the right amount of fuel mixed with the right amount of oxidizer at just the right time. In fact, the fuel injection system ultimately involved 18 separate injection chambers in 2 concentric circles, and it was described by one of the principal designers as a plumber's nightmare. Even the shape of the combustion chamber was the subject of much design experimentation. Early on, it was assumed that the chamber needed to be fairly long to ensure that there was enough time for complete combustion so that unburnt fuel and oxidizer were not being spit out in the exhaust. But in the end, as the cooling and injection methods improved, it was found that the combustion chamber could be shortened until it was almost spherical, and critically, also much lighter. So the bang phase of the rocket sequence eventually converged on a spherical chamber fed by 16 injection chambers that mixed the alcohol and oxygen that had been circulated around the outside of the chamber to cool it. A small amount of alcohol was also diverted to provide film cooling of the chamber. Once the details were designed and refined, the motor was actually very reliable. Reliable enough, in fact, that the same basic concepts are still in use today. So that's the bang and the blow sorted. What about squeeze? Why is that even an issue? Well, when you consider that the basic idea here is to encourage the reaction products in liquid form to enter a chamber in which combustion is occurring at high pressure. Doesn't sound all that straightforward. It gets less straightforward when you consider that you want to encourage this flow to be reasonably uniform, even as the propellant tanks go from full to empty. It's even more complicated when you consider that the method of providing this encouragement must be as light as possible. Early designs, and even some modern ones, used a system of pressurizing the propellant tanks with an inert gas, almost always nitrogen. Effectively, you would just connect a high-pressure tank of nitrogen to the upper end of the fuel or oxidizer tank, which would push the fuel or oxidizer out the bottom end when a valve was opened. It was a simple solution, but it was not really very light, especially as the size of the motor was scaled up. Because you see, the propellant tank got bigger, so the volume of the inert gas had to rise accordingly. Moreover, that volume of nitrogen had to be maintained under high pressure in order to provide enough encouragement to move the fuel or the oxidizer into the high-pressure combustion chamber until it was completely empty. Maintaining a large volume of gas like nitrogen under high pressure requires a very strong tank, which in 1940 meant a lot of high tensile strength metal, which meant a lot of weight. Weight that was all wasted in terms of the rocket equation. So another method had to be found. The obvious choice was to use a pump of some kind to pull the propellant liquids out of their tanks and push them into the chamber. The most efficient kind of pump for this job was a turbo pump, which sounds complicated, but honestly the common table fan is probably the simplest example of this kind of pump, because a turbo pump is really just a set of spinning blades that suck liquid in one side and spit it out the other at higher velocity. But of course, there is a bit of a difference between the fan in your living room and a turbo pump that has to move more than 100 pounds per second of liquid oxygen. The design that was used in the A4 was actually to use steam to drive the pump turbines. This sounds kind of old-fashioned until you learn that the steam was produced by, quote, mixing concentrated hydrogen peroxide with sodium permanganate catalyst. Huh? Yeah, like I said, there's a lot of chemistry in rocket science. Chemically, hydrogen peroxide is what you get if you add an additional atom of oxygen to a water molecule, its chemical formula being H2O2. When it is mixed with water in low concentrations, like about 3%, hydrogen peroxide is an effective bleaching agent and antiseptic, and you might have some in your medicine chest. In high concentrations, however, it is thermally unstable and decomposes into water and oxygen, releasing a significant amount of heat. This thermal decomposition can be encouraged or catalyzed by various chemicals such as the aforementioned sodium permanganate. So essentially, the A4 took hydrogen peroxide, passed it over sodium permanganate crystals. This caused it to dissociate into water and oxygen, generating enough heat in the process to vaporize the water into steam that was then used to drive the turbo pumps. Once again, the description of the final solution sounds pretty straightforward, but considering that we are talking about a system that uses a large amount of liquid that is described as violently explosive under the right or wrong circumstances, and that the whole point was to use it to generate large quantities of high-pressure superheated steam, it is fair to say that developing this system must have had its moments of high drama. Okay, but now we have the whole cycle of squeeze, bang, blow sorted out. What else could go wrong? Well, this is where we need to remember that a rocket is a lot more than just a motor. Even if it goes to space, it's a lot more than actually just a spacecraft, because in point of fact, rockets spend a very important phase of their lives being an aircraft that travels very quickly. In fact, for a long time, the A4 rocket was likely the fastest man-made object there has ever been, probably by almost a factor of 10. This is what engineers call a highly non-trivial problem, particularly if it's the first time anyone has ever done it. In other words, figuring out first of all how to stabilize the rocket at such speeds under such aerodynamic loads was a significant problem. Figuring out how to guide it while it was in flight was an even bigger one. Bear in mind that this is in the days before digital computers and barely into the age of television. Now, strangely enough, the Germans had developed and even used a remotely piloted vehicle in the form of a gliding bomb that was guided from an airplane, which they used to attack ships. But piloting a glider from a few hundred meters away while traveling at about the same speed is a whole other world from trying to fly a rocket that travels hundreds of kilometers and recedes from view at Mach 2.5. In fact, while the A4 program solved the stabilization problem with some truly fascinating mechanical engineering that is just too complicated to go into here, they never really did solve the guidance problem fully. And one of the reasons why the V-2 was pretty ineffective as a weapon was that it was horribly inaccurate. So, at the end of the Second World War, after a truly massive amount of research and development, Nazi Germany had produced a rocket that was an impressive technical achievement, although it was really not very useful as a weapon. However, the truly mind-numbing destructive potential of combining the A4 ballistic missile with the newly developed atomic bomb was not lost on either the Americans or the Russians in the period immediately following the war. Both the United States and the Soviet Union embarked on projects to find and acquire the designs and data regarding the A4, also the scientists, engineers, and technicians who had designed it and built it. And that is how the basic design that originated in Nazi Germany became the basis for not only the early ballistic missiles in both countries, but also the basis for the rocket which, on October the 27th, 1957, launched the very first man-made object into orbit around the planet. This was, of course, Sputnik 1, the very first man-made satellite. It was launched from what is now known as the Baikonur Cosmodrome in Kazakhstan. This event precipitated the great space race that eventually saw the first humans in space, in orbit around the Earth, and eventually, of course, on the surface of the Moon. But that piece of the journey is going to have to wait for another episode. In this episode, on rocket science, we have looked at how humanity developed engines with enough power to lift our creations off the planet. In the next episode, we'll look at how we developed the means of controlling that power so that we could have accomplished the feat reliably. The next installment of A Terranauts Guide to Leaving the Planet will follow the great space race and how it transformed the rocket from a means of throwing explosives at one another into a vehicle for taking humans and our inventions off the planet. That episode will probably be episode 1 of our second season that will likely begin in September. I'll provide some more of the details next time in our final episode of this season. For now, thanks again so much for listening. Please remember to support the podcast with one of the 4 R's. Rate and review the podcast on your podcast server, respond with some feedback, or recommend the podcast to a friend. Thanks again, and we'll talk to you soon.